Welcome back to the fourth module of the electronic structure simulations for communities at large scale facilities course. With the fourth module today. My name is Timo. I'm a first year PhD student of Giovanni and Nicola. And today I will guide you a little bit through the more advanced settings of the app. So to show you a little bit the program of today. So maybe a note before, so maybe you can already start to access the server yourself because it will take some time and I will explain the program so you can already access the link. And also already a note, the Azure server is now also open for users online so that you can also check it out yourself. So for today, I myself will start with an introduction or like a practical introduction in how to use DFT+U to model ferromagnetic and antiferromagnetic systems with the AIDA lab. Afterwards, Miki will explain how to calculate phonons and neutron scattering. Afterwards, we'll have an introduction into Raman spectroscopy by my colleague Andres. Afterwards, Miki picks up again and explains how to use our workflows to calculate the stopping sites for Muon spectroscopy. And finally, Xing will talk about Bader charge analysis and give an outlook, basically how to continue yourself at home. And Giovanni will also showcase the more advanced or additional workflows on spectroscopy and automatic calculation of DFT+U parameters. As I mentioned in the beginning, also for the online users, you can also access the server. And one important note, so we will close the server tomorrow around lunchtime, basically. All the data will then, of course, be deleted. So save your data when you, in case you want to keep it. And there's also an AIDA Lab demo server so that you can also, after the school still can continue at home and try things yourself. And with this, just as a very quick motivation, as I mentioned today, my talk will be about modeling magnetic configurations and DFT+U. So basically, we will see how we can model ferromagnetic and antiferromagnetic phase of cobalt oxide. And with this, I would say we start the practical part. So you can now all access the AIDA Lab, I hope, and we start by simply clicking a new calculation. Similar to what you've already been seeing in the first part, we prepared in-app guides so that you can easily follow it yourself or repeat the things afterwards. So maybe also in case you get lost during this presentation, no worries, maybe just follow it, see how we do it. And there are all these guides, in this case, in the point relaxation and electronic structure. So we prepared one guide, advanced settings, that I will basically skip explicitly here, but mention a few things while doing the magnetic calculations. And so we start with the ferromagnetic one. And as you can see, once you activate it, you see all the instructions. So again, you can also do it yourself afterwards. So the first part will be about ferromagnetism and DFT+U, and we also recommend to do this as the first one before you move to the antiferromagnetism. In this case, we will model the projected density of states because this is a handy property to understand the electronic structure, to also easily see the impact of the Hubbard-U correction, and also, of course, get a sense of the magnetic behavior of the material. For this, we start with the first step, selecting the material we are interested in and that we want to study. In this case, we go to From Examples, the simple crystals, and select cobalt oxide. Here you can see the unit cell as already shown last time. You can inspect it. And this will be also more important for the antiferromagnetic one. But for now, we simply confirm and move to the next step. In the interest of time, we will skip the relaxation here. So we will just select structure as is, which means, okay, we just take the structure without any optimization of the positions or the cell. Of course, when you do the simulations for your real research, it's always recommended to do relaxations to adjust to your functional or the desired accuracy. This next step, we select the properties that we want to calculate. As I mentioned in the beginning, we are interested in the electronic projected density of states. So we just tick this checkbox here. And finally, go to the Customize Calculation Parameters tab. Again, for this tutorial, we select the FAST protocol. As you've already heard last time, those are parameters that give results that are okay to get a first sense, but of course for your research you should at least use the balanced one. But in the interest of time and the resources, we just choose the fast one here. We are interested in magnetism, so hence we of course activate magnetism here. You already see this note here that in order to tune or set up your initial magnetic configuration, we need to go to the advanced settings, which we will do in a second. Just as a side note, for practical purposes, we keep metal here, which is also reasonable for our system, but even for insulators, it might make sense to keep metal activated, because if you want to determine your magnetic moments self-consistently during the calculation, this is necessary. When you select insulator, you only have the possibility to fix the total magnetization of your cell. But we can just, to show to you, once you do this, you immediately also get this note, so everything is basically explained. But again, for now, we choose metal, activate magnetism and the fast protocol. Afterwards, we go to the advanced settings, and here we basically are interested in defining our initial magnetic moments. As I mentioned in the beginning, we also prepared a guide on advanced settings on how to tune them. So I will briefly go through them, but we don't touch them really in this tutorial. So what you can in principle do, you can of course also model charged unit cells. This will be also, or is partially important for the Muon spectroscopy, for example. You can adjust your convergence criteria either for the self-consistent determination of your charge density or during ionic relaxation. Of course, also maximum number of steps, etc. Of course, these, especially the thresholds, have a huge impact on the cost of your calculation, of course. You can in principle tune the smearing and decay points, but as you've heard last time, we already provide a good set of parameters here and well-tested ones. And this brings us then to the actual magnetization subsection. As I said before, so in principle, you can set either the initial magnetic moments or the total magnetization. In this case, we will set the initial magnetic moments and calculate the actual magnetic moments self-consistently. You can just enter this text field and we set it to 3 Bohr magneton. And for oxygen, we keep this default value. So as you've already seen, in principle, we also provide some default values here. As I mentioned, we are interested in also including the DFT or the Hubbard U. So for this, here's this checkbox that we need to activate. And then we can also define the U values for the different elements and orbitals we are interested in. In this case, we set the cobalt U value to a value of 6 eV. As you will see in the Outlook, there are also dedicated workflows that allow you to calculate this or appropriate U values self-consistently from first principles, but this is kind of beyond the scope of this tutorial. For the oxygen, we don't define a U value, and in principle, but this is more advanced. For now, it's fine. You can also define eigenvalues. So this means you can actually define basically the occupation of your, or the starting occupation of your Hubbard or the matrices. And this is important to converge to certain local minima, for example. But for now, we will just keep this set up. And finally, we also, for each property that we calculate, we get this additional tab here. In this case, we will adjust the energy grid step to 0.03, just again for the in terms of time. And that's basically the setup for this calculation. And so to set up ferromagnetic calculations. And with this, we can confirm it. In principle, you could now submit your calculation, but we won't do it this time. We'll just import the examples and show this again to inspect the properties, because we will run a bunch of calculations during all the different tutorials. And since we have limited computational resources, you can anyway only run 1 or 2 jobs in parallel, so they will anyway get stuck. So that's why we basically stop here. But in principle, you could just click the submit button, and as you've seen last time, you would be then forwarded to the last step. So now, let's now actually import the results of this calculation. So for this, you go back to the landing page of the AIDA lab, of the AIDA lab, and we then go to download examples. Oh, it's mine. Okay, sorry. You go to the landing page and then download examples. Ah. I got kicked out. Yes. Okay, now we are back, right? Okay. Yeah, so basically when you get to this examples section, we can then see here these four examples dedicated to cobalt oxides and the tutorial we are doing right now. So we can already import all of them now and inspect them step by step afterwards. So you can see they also have dedicated labels, but we will see this in a second. So you can select them by just, depending on your system, clicking Shift or pressing Shift and just clicking them, or you can also just click with the mouse and drag basically. And once they're all selected, you can then press this import button, and then you will see that step by step, all of the calculations or examples are imported. Exactly. Once this is done, so probably this might take a bit longer for you. We can then go to the calculation history indicated there, which is basically the list of all jobs that you've been running before. But also, since we now imported the calculations, you can see that you will also have these entries run at the 4th of April with the dedicated labels, which are the calculations that we just imported. And as Giovanni has also shown last time, you can provide specific labels. So we can see, for example, the one that we just submitted in principle is the cobalt oxide ferromagnetism with the how about you. So we can just click on this ID here, and then it will open the corresponding AIDA lab page, basically, of the calculation. And then you will in principle see everything that was done to execute this calculation. But this has also already been shown last time. So we can directly go to the status and results here. We can then again see the system we are studying, go to the electronic PDOS tab, and immediately see here our results. Just again to remind you a little bit of the things that you can do in this results widget. So in principle, we can then group either by the element. I mean, in this case, we only have one site per element, but we can then also define different groupings. For example, we can group per element and also show each orbital separately, for example, which takes a bit longer to load. Exactly. And then by interacting with this widget, so for example, double clicking on the cobalt 2PZ here, we can then basically inspect them and also move around here. Okay, this is not the best example. But for example, also now we can just revert it, or the cobalt 3D states, which are located here. We can then interact and inspect how or where certain orbitals are located and understand better our electronic structure. And you can also on the x-axis, you can just drag and to basically adjust the range. Okay, so that's basically it for the ferromagnetic tutorial. Next, we move to the antiferromagnetic one. So we can just close this tab. And maybe we could just go back to the landing page. So from here, we just start. Yeah, I mean, sure.
See the calculated at the end. I guess at any stage you can say how do you know what the magnetic
Yes, you can inspect this in the parameters, but there's Yeah. So the question was if we can now also basically inspect the obtained magnetic moments, since we calculated them self-consistently, and we can do this in the yeah. I just closed the example. So in principle, you can inspect this also in the output file, but they are also parsed and yeah. There. They're also parsed here. Okay. Yeah. So exactly. So in the output parameters, you can get the total magnetization or the absolute magnetization. But if you are interested in the actual magnetic moments per site, for example, then you would need to go to the output trajectory. But this is not directly parsed here. I mean, this is then something that you would need to inspect in more detail, basically. But in principle, they are also in the output file. You mean that, so you would like to have basically that yeah. I mean, this is something we can basically, I mean, we will consider to also make this accessible, but right now it would be.
I think it would be other time.
Yeah.
Information. I think it's a very valuable.
No, for sure. But yeah, I mean, the comment was just to make it directly accessible in principle, that you can immediately see it in the results tab also to, I mean, when you do magnetic calculations, it's of course reasonable to directly inspect the results. Yeah, thanks. Anything else or? Okay, so then again, we go to the landing page of ADA Lab. We start a new calculation. And this time we want to model now our antiferromagnetic example. So we click again on tutorials, the relaxation and electronic structure, and then select the antiferromagnetic guide. And for the antiferromagnetic guide or these calculations, we need to adjust our structure a little bit, because for antiferromagnetism, you want to have, I mean, one spin up and spin down component basically for the same element, for example, in this case for cobalt mainly. But our unit cell only contains one cobalt site, and to kind of artificially create these two groups of cobalt, the spin up and spin down, we first need to double our unit cell. So to create a supercell that we have at least an even number of cobalt sites. I mean, of course, if you, I don't know, calculate a different chemical compound, then of course you might already have an even number, then it's fine. But for this example, it's necessary to create the supercells, and then we will define the two different groups of cobalt atoms. And you will see later that we can then assign different initial magnetic moments for these two groups. And this is what we will do now. So first, we do the same as before. So we go to From Examples and select cobalt oxide. Next, we open this Edit Structure panel. And here in the Edit Cell tab, we apply now a transformation to the cell to create a supercell. So we select a value of 2 here to basically double the cell in direction of the third or along the third lattice vector. So we click Apply Transformation. You immediately see here that the chemical formula gets also adjusted because now we have the supercell. But it's important to note that we only click this button once, because otherwise you will always apply the transformation again and again, and in principle exponentially increase the size of your structure. And as we can also see here now in this View Structure panel, that indeed we created this supercell. The next thing to actually define the two different groups is we move to the Edit Atom Tags tab over here. And now we want to select the cobalt atoms and assign them to the different groups. So for this, we can just click here. So you just click once, and then the selected site should turn green. And afterwards, we can then click from selection here, and it will automatically get the correct index of the atom in our unit cell, because this might be not, especially in larger structures, this is not obvious. So for the first one, we select or we set the tag to 1 and just click update tags. And then we just repeat the same for the second cobalt atom. We click on it again. We press from selection again. And then this time we set the tag to 2. And afterwards update it again. And in principle, this index list here also supports slices. So if you type 1.4, which would be selecting 1, 2, 3, 4, you get this table that is scrollable. And you indeed see that cobalt has now 2 different tags, so 2 different groups, and we have no group, or we have just 1 group of oxygen sites. So with this, we are done with the preparation and just confirm. And now we almost follow the same steps as before. So in the interest of time, we don't run relaxations. We are interested in the electronic PDOS. And now customize our specific parameters. So indeed, we turn on magnetism again and switch to the fast protocol. And you immediately also see this warning here, highlighting basically that AIDA Lab detected multiple groups or tags for 1 chemical element, and that you might be interested in antiferromagnetic systems, and that you need to tune the advanced settings for this. And this is what we are doing now. So we go again to the magnetization section here. And what you can see here, before we only had cobalt and oxygen here, but this time we have 3 rows for each so to say species. And this time we set cobalt 1 to -3. We keep oxygen as is and set cobalt 2 to 3. And this way we break the symmetry and define our different initializations. And that's it basically. So in principle, you can also define the activate the U here, but for now we just keep it as is. And finally, just again set the energy grid to 0.3, and afterwards we can confirm. So the main difference, as you can see, is basically so how to tune the parameters is basically very similar, but the main difference is that you might need to tune the actual structure. Same as before, so we don't submit this time, and in principle we can also now just inspect the downloaded examples again, because we already downloaded all of them. But since we want to compare them, I will just move back to my slides, because in principle we'll just do the same thing again, inspecting the PDOS in the result widget. So going back to the slides here, or are there any questions on the app right now on the procedure, or was it clear, the changes? Okay. Otherwise, feel free to ask at any point. So to inspect basically what you will see when you run the results yourself, or you can of course also just inspect the downloaded examples. So here we see the ferromagnetic configurations here without a Hubbard U, and here after including a U correction. And what you indeed see is the expected kind of upwards push of the cobalt states here. In this case, we don't have a gap in the system. And of course, also this is still with the fast protocol. So when you adjust the parameters, you might get slightly different results. But otherwise, you basically get what you expect and see the effects of the DFT plus U, and also learned how to do this. And the same for the antiferromagnetic one. Indeed, we have this antiferromagnetic shape of the projected density of states, so no total magnetization. And we basically observe the same effect of the Hubbard U, so basically an upwards push of these states here, and also, of course, a rearrangement of the states in the valence region. With this, we are basically at the end of this first module, or the first guide. So basically, you learned how to model different magnetic configurations in the app, so how to set your initial magnetizations and what you need to change for antiferromagnetic calculations. You also saw how to enable DFT plus U and how to tune it, and also again how to work with existing examples. And as always, for all the guides, we also prepared a set of post guide exercises, so feel free to also continue there and play a little bit around. So yeah, if there are no further questions, it's yeah.
Maybe a small question.
Sure.
The U parameter, because now we just said it, what is that? I want to know if it's a similar story as with the pseudo potentials, as in there's Ortega-Guerrero, for example, or where could one still have a good idea of what
Yeah.
number to put in there?
Yeah, so the question is how you would, yeah. So just to repeat for the online attendees, so the question is how to choose the U value basically, or where to find good references. And of course, one approach is always that you just check for, I mean, if you're interested in a specific system, you look in the literature and see what people did there. And typically, I mean, you get values around 5, let's say. But in the end, this is really depending on the on your chemistry, on the local environment, etc. And that's why what we will also show towards the end how you can calculate them actually from first principles to get safe persistent UMV values. Because indeed, this is also part of the post exercise. You can also just play around, set 4, 5, 6, for example. You will indeed see that this, of course, affects your properties. I mean, sometimes people also determine basically empirically, so to say, that you, I mean, if you're interested in a band gap, you tune the U value so that you reproduce the band gap. But of course, in this way, it's not really ensured that this also works then for, I don't know, thermodynamic stability, for example. So, yeah.
Thank you.
Sure. Anything else? Okay. So I just stop sharing, right?
Okay, so now I will show you a demo on how to compute phonons and inelastic Newton scatterings within the IR Quantum Espresso app. So basically, first principle simulations of lattice dynamics is a very powerful and complementary tool, no, to help the interpretation of complex experimental spectra. And in particular, what we can obtain from first principles are mainly 3 quantities, so force constants, Raman tensor, and Bohr effective charges. And by computing these 3 quantities, we can then obtain phonon dispersion, Raman infrared spectra, and inelastic Newton scattering cross sections. Particularly here, I will show you the first and the third quantities, and for Raman and infrared spectra, you can see the demo by Andres just after me. So now I will go to the app. So we start as before from the landing page of IDA Lab. We click on new calculation. And now we can activate the tutorial on phonons and inelastic Newton scattering. So we select phonons, and then again, this is already selected. So phonons, thermal properties, and inelastic Newton scattering. So the system that we want to simulate now is just simple bulk silicon, just in interest of having a lightweight simulation. So we go to step 1, and then we open the From Example tab to search for our bulk silicon. We go to this drop-down menu, and then we select our structure. We can see that indeed this is our silicon. We can confirm it. And now we go to step 2 to configure our workflow. Particular, in this case, we want to run a full geometry optimization. This is crucial if we want to compute phonons, because if we don't have a geometry which is optimized, we will have unstable phonon, basically, so negative phonons, negative frequency phonons. So basically, when you do phonons within the app, always do full geometry relaxation step. Now we can select on step 2.1 our property that we want to compute. So we tick vibrational spectroscopy phonons checkbox. And we go to step 2.2. So in basic settings, as before, basically we select the fast protocol. And we can, in this case, we can select the insulator. electronic type, as we know that, I mean, silicon is an insulator. And then we can skip advanced settings. We don't need to set anything there. Everything will be already set up by our protocols to default values. We open vibrational settings tab, and here we can tune the parameters for our Phonon calculation. So basically, what we can, what the first thing that we can select is the type of simulation. Here we have 4 simulation types. We are interested in the phonons for non-polar materials and inelastic Newton scattering one. Then if you are interested in particularly in Raman and IR spectra, you can see after me Andres doing that. So particular, I didn't mention how phonons are computed within the app. So basically there is an underlying AIDA workflow which takes care of computing the first constants of phonons by means of several finite displacement calculations, where then forces are evaluated and are used to compute the second derivative of the energy with respect to atomic displacement. And so we need to set a supercell size for our system to host all the single displacements. So here we can select supercell size. We can ask if we don't have an idea on the size of the supercell that we need, we can ask for a hint, which is based on our knowledge of the problem. In this case, we will just stick to a 2x2x2 supercell, still in interest of time. This is usually a fairly good starting point to compute Phonon dispersions. We can also estimate the number of supercells that we need to evaluate. In particular, in this case, in the case of silicon, the supercell will be only one, thanks to symmetry arguments. So basically, all the possible atomic displacement will be basically a symmetric replica of just one of them. And then we can confirm. So now we are on step 3, where we can select the computational resources for our simulation. We can see that here now we have, of course, a PW code, which is the main code to run DFT by means of quantum espresso. And we have also PhonoPy, which is a Python code which is used in the AIDA workflow to compute indeed the force constants and Phonon dispersion as a post-processing step. As before, we don't submit, but we just load a pre-computed example. So we can go back to the AIDA Lab homepage. And we go again to download examples. So also for phonons, we have several examples already pre-computed. In particular, what we want to download and inspect now is this one, where the label is basically phonons plus INS, as you can see here. So we can import it. And then we can open the calculation history page to see if you can find it and open it. Indeed, here we see that we have the examples that we just downloaded. We can open it by clicking on the ID number. And then we are basically landing on the page with the same page of new calculation, but with all the parameters and the results of the simulations already loaded. So you can see here we have basically a possibility to visualize the initial structure and the relaxed one. In this case, they are not so much different because silicon was already basically in the optimized geometry. Then we can switch to the vibroscopy tab of results, where we have mainly 2 tabs in this case. So the first one is phonons. First result is, of course, the Phonon dispersion that we can inspect interactively in the same way as Timo showed for bands, for density of states. We can download all the data to further post-process results if we need to open them in another software of your preference. The same for thermal properties, which are computed using PhonoPy code, so Helmholtz free energy, entropy, and specific heat at constant volume. And then we can go to the last tab, where basically we compute live the inelastic Newton scattering. So we can just start the initialization of the calculation. And depending on the size of your system, this will take a while. But in this case, just 3 seconds. And basically, the results of Newton scattering are divided in 3 tabs. So the first one is single crystal, where we can observe the structure factor in the same Q path of the Phonon dispersion. Then we have the powder sample, which is where basically you can just observe the structure factor as a function of the vector, the modulus of the Q vector. And then we have also the possibility to visualize the structure factor for fixed energy section of the reciprocal space. So for each of these tabs, we have several parameters that we can tune to modify our plot. We can, for example, change units. We can also basically change the size of our step in Momenta path to have, let's say, a coarser or a finer grid. We can change the number of energy beams that we use to sample basically the energy of our spectra. So for example, you can go to 1000, and then we can plot. So you see that indeed our plot is much better, let's say, is much refined. Also, in this case, we can download all the data. Basically, we will download PhonoPy data that can be used in other software, like, for example, in this case, all the results that I show you here are computed by means of the euphonic code. I don't know if you know it, but basically you can just download the data and compute again the Newton scattering. So basically, this is basically everything I wanted to tell you about phonons and Newton scattering. So if there are questions. No? Okay. Yeah. I will just close now there.
Okay. Okay, so good afternoon. So I'm Andres Ortega. I'm also a postdoc at Empa and part of the IDLab development team. And I would like to, let's say, show you how you, in case you're interested of computing Raman or IR spectra, with a few pointers of maybe how it can be used for your personal cases. So as you mentioned, as it was mentioned by Miki, in this case, we can compute phonons, and now we need also the electric response. So we need to, let's say, have everything in a gigantic workload that we have. However, in the app, we make it a little relatively easy. That is a couple of clicks. So again, we are going to set up a new calculations. And in order for you to not get lost, let's activate the pages or the in-app guides. We're going to go here to the Phonon part and the IR Raman that you can follow. So as you've been seeing, the app always behaves in 4 steps mode. Usually it's going to be the first one of interest is to set up our structure. You can upload any kind of differences, but I would like to bring your attention that we have implemented this app that it can handle actually different periodicity of the system. Since I'm used to work with graphene nanoribbons or maybe slabs, you can actually go and have a bunch of different features here in the edited structure that you can set up the periodicity, or if you want to shake and so on. And since we're interested in maybe the Raman, you should take into account that the symmetry of the system you're putting, or the initial part, is a little bit important. And in your case, if you already know that maybe you're losing symmetry, to something to take account. So in this case, for the purposes of time, we will select again our best example, that is silicon. And then we will, let's say, confirm this structure. So now here for the Raman, we're computing non-resonant Raman, meaning that we are not taking into account any enhancement out of an optical excitation. However, from my own personal experience working with different colleagues, even though it's non-resonant, it's at times really good enough with the comparison because it's only an enhancement of the peaks. So again, in the second part, when you're using your own systems, as Miki said, I would recommend that you have a system that is already really well optimized, meaning that even though for the tutorial you're using the option of fast when you're doing your own examples, for this particular, it will be really important that you use a stringent to optimize. Again, for the purposes of the calculation, we will use fast. One point that you should have in mind is that you first should know the electronic properties of your system, because for this part, it is important that your system, at least at the DFT level, has a bandgap. So for example, you saw that Timo explained about the DFT plus U, and maybe it was metallic. So it is important that you address the electronic properties in the sense that maybe you need a DFT plus U to open the bandgap. That is a known problem, or that you know that it has relatively enough bandgap because you will be applying for purposes of computing the polarizability response electric field. And it is important that the system has a bandgap. How small? Maybe you're wondering, maybe even up to 0.3, because I work with graphene nanorobots, and even at that small, it is relatively, it behaves well. So for example, when you're working in this part of the advanced settings, you should mimic all the conditions that you use for your electronic properties. They should be actually reproduced. Maybe if it has a spin polarization, set up all of these details. And for example, it's really important when you were doing your geometry optimization that since it depends on how well optimized it is, you can always have this convergence threshold that you can play. For the purposes, again, of here, we will not play around, but when you're working with your own system, I would recommend that the thresholds of this convergence should be to 1 to the minus 13 and so on. Then if you put a stringent, it will go to those levels. Now, for the vibrational settings, as Miki said, we are using this plugin developed within the AIDA team. And in this case, we have two choices of how we're going to get the Raman. Now, we can actually, the app offers an option that you can actually compute everything, in which we get phonons, Raman, IR, and even the inelastic neutron scattering. And this is because we displace the atoms. Basically, we get the vibrational modes. And now in the dielectric part, we get all the components to build basically everything. So in our case, we would use the simple primitive cell. This is, in most of the cases, fine because Raman are more important at the gamma point. So the primitive cell is enough. However, maybe if you're working with a bulk system and you want to converge the vibrational mode, you can make it bigger. In this case, we have this symmetry tolerance, which usually is automatically set up. But in case maybe you're working with a system that maybe lost a little bit the symmetry, maybe this is too tight, you can actually make it a little bit bigger. So then you can actually find symmetry in the modes and they will be reflected in your spectrum. So let's say we can confirm here. And now we come to the part of the resources. And for this example, this is more than enough. But then I want to give you a little bit of tips when you're working with your own systems. And usually, as we explained, we have the phonons in the dielectric part, and the phonons tend to be relatively cheap in terms of computational resources. So you can actually control the amount of resources you want. But for the dielectric part, it tends to require a little bit of extra memory and resources. So the good thing is that you can actually already select, depending on resources that you have access to actually maybe put a little bit more for the dielectric when you're working with a big system and so on. And even you can actually set up the time. Here, for example, once you use it, you can actually set up the time and maybe even increase the time for the dielectric because it might be required. And actually the phonons tend to actually be quite fast. As Miki said, PhonoPy is a post-processing tool, so it doesn't necessarily require a lot of resources, just to keep that in mind. So again, we will not submit, we will use the examples, but I will always advise you to pick a relatively good name because as you've noticed, the jobs start piling up. So it's always good to put a proper name. So we go here to download and examples. And wait just a little bit. And we go and five here, this one, right? And then we are gonna use our example. Okay, now we go quickly to our calculation history. And we are gonna open it, which is here, okay? And then I will wanna maybe guide you a little bit in the results panel that if some of the others are experimentalists or even for computation, like maybe more of your interest of how to get the results and so on. So again, we come back again to the tab that is dedicated for the results. So in this case, we have this panel in which we can actually compute a powder spectrum, meaning that we are computing actually all the different directions of the system. It gives you like a powder thing. For silicon, since it's highly symmetric, we have a triple degenerate, so it's only one peak. We don't have IR, as it is known because IR passed through silicon. But we can also use a single crystal spectrum, and this is really important because you can actually try to match with experimental conditions, because maybe you have on a specific plane, and then this is important that you set up these directions that you can compare with your experiments. Usually we have also this option of analytical directions. This is quite important when you have polar systems, and then like that, it is important that you align it with your incoming light. And here's the spectrum. It will appear in different, well, I mean, in this case, it won't change too much, but usually you can set up, if you want, usually in this, it doesn't apply so much, but you can actually have the polarized. Here, you will have like your proper polarized and depolarized data. If maybe you want to compare for the symmetry of the vibrations, here you will have a list, and that's what I was talking about, the symmetry, because here usually you will get the symmetry of your vibration, and again, as I said before, it's triple degenerated in silica. Then of course we can actually visualize a little bit the vibrations. So then like that, it is maybe it is important that you want to analyze actually what is the vibration, and in this case, well, we have them animated, and then when you wanted to compare with your system, well, it will be easy. The other tab is if you want to maybe get a little bit information about the dielectric tensors, about the Raman tensors per atom, or you can download this data and well, you can analyze it if you want to upload it in your own program of choice. And basically this is the tutorial. I will go here and set up this again, and you can maybe have a second exercise, maybe for silicon oxide, and I'm really happy to answer any questions that you have. Yes.
You said that it's very important to have consistent settings between your calculations you did for the electronic part and then the subsequent phonon calculation. Is there a way to transfer these settings between? Like I started a new calculation and I want to base it from something in history.
So the question was that I mentioned that it is important to try to replicate the conditions of the electronic properties, the settings for the Raman. At the moment, we don't have this feature, but the main message that I wanted to, let's say, give was more into that you have the answer that you have a band gap in your system, because it's important. And or maybe, for example, at times a system don't display a band gap if you are working as a closed shell, no magnetization. But maybe once you put magnetization as antiferromagnetic, you will actually open the gap a little bit. So that you, let's say, remember these details, otherwise you will not, let's say, get a system with a band gap and no replicate. But in the future, we might include this kind of preloading of a previous one. But at times, this is, I'm saying this as tips, because usually the protocols that we have, such as string and so on, are already settings that are really well enough. But this is just in case, so maybe Timo was showing that the system might be antiferromagnetic and have these details. And then in this case, you might need just to be extra careful. No? Okay, so thank you for your attention.
Okay, now I will show you how to compute to do Muon spectroscopy by means of our app, particular on how to compute Muon stopping sites of material. Why? The reason is that the determination of Muon stopping sites is something which is very difficult, but it's possible, of course, to obtain by the experiments. But in first principles approaches is in principle straightforward. In particular, we can employ the so-called DFT plus mu, where basically we compute DFT simulations on a material where we put a muon as an infinite dilute defect in the cell. So once we predict these muon stopping sites, we can easily compute the magnetic interactions, the local magnetic interactions, such as bipolar fields and contact fields, as you see here in these equations. And in the app, what's happening under the hood is that we have an AIDA automated workflow to compute muon stopping sites, which is which is depicted here on the left. You see, basically, we start from the input lattice of our system that can be also magnetic. Then the workflow automatically generates several interstitial trial positions. And after that, it computes for each of the trial sites the relaxed optimized geometry of the supercell of our system plus the defect inside. And so at the end, we can basically analyze all the resulting sites and classify them with respect to the total energy. And we can also compute several quantity of interest, like the distortion induced by muon and the polarization function of the muon spiral polarization. So now we'll show you the demonstration in the app. So we go again to a new calculation. Now we activate the in-app guide about muon spectroscopy, and in particular, here I will show you only how to compute stopping sites. Then if you're interested, you can follow also the second guide about spin relaxation function. So for this case, we will use, let's say, a very well-known structure, which is lithium fluoride. And to load the lithium fluoride structure in our app, we basically will use the Optimade client to obtain the structure from a given database that we have available on the Optimade. So we click on Optimade tab. We start loading the Optimade widget. So we set up all the architecture to perform our query. As provider, we select Materials Cloud. And as database, we go to the MC3D, which is a large data set of three-dimensional curated crystal structures. So now we are loading, basically, the database query. This may take a while because it needs to connect and to receive a response from the server. But now we are ready. Basically, we can select our structure by selecting only the given elements in this interactive periodic table. So we select lithium right here. Then we can search for all the possible structure that we may have. We have several of them. The one that we are interested in is the first one that you see here. In particular, for the muon simulation, we want to start from, let's say, a conventional unit cell. And we can do it by starting from this unit cell and basically from this primitive cell and basically using our eddy extractor tools to convert to a conventional one. So you see that here we have now the conventional unit cell. So now we are happy with that, we confirm it. Then in this case, we will skip the geometry optimization. The reason is that we will perform geometry optimization in the Muon workflow. So we will perform geometry optimization with also the Muon inside. So we can also skip this pre-processing step now. Now we go to step 2.1. We select the Muon spectroscopy checkbox to activate the tab in step 2.2, as you can see here. Also in this case, we select fast protocol and insulator electronic type. And then we go to the Muon settings panel where we can set up all the parameters for the Muon simulation. In particular, we can select different properties that we can compute. For example, by default, we always enable the search for Muon stopping sites and the corresponding polarization for each of the sites. In this case, we don't want to compute the polarization, we just compute the stopping sites. So we deselect this checkbox. As you can see, when we deselect the compute polarization checkbox, the polarization settings will disappear because we don't need them. But in principle, what you can select in the polarization settings are the value of the external field that we can apply to the system to study then the response of the Muon spin. So we have basically a range of field that we can select. We can also change the step between all these values. So for example, if you put 10 and we go from 0 to 50 millitesla, we will obtain only 6 fields values. Then about the Muon stopping site settings, we can basically select the Muon charge state between positive Muon or neutral Muon, so Muonium, if you are interested in this case. Usually we stick to the charged Muon. So as the Muon is basically a defect in our system, also in this case, we need to select a supercell to host the Muon in such a way to avoid interaction between the replica of the cell. We can ask for hints also in this case, or we can just stick to the unit cell, as we will do now for computational reasons. Then we can custom the key point distance, so basically the density of our mesh grid on which we want to compute the DFT simulations. In this case, we will just put a large value in such a way to just compute the DFT at the gamma point. This is not accurate, it's just a way to have to make the simulation faster. So usually you can stick to the default value, which is 0.3 angstrom, inverse angstrom. We can disable the Hubbard corrections, if any, and we can also enable or disable spin polarized DFT if our system is magnetic. Then another crucial parameter for our simulation is basically the density of the Muon trial site in our cell, because this basically determines the number of simulation that we are gonna submit. So for a given Muon spacing, we will have a given number of Muon trial sites. In this case, if we put 1 angstrom for the, let's say, the grid spacing of all the single Muon sites, we obtain only 3 trial configurations that we can visualize all at once in our unit cell. You can see that the 3 trial Muon sites will be these 3. We can also change it. I mean, we can put, for example, 0.7. And in this case, we will have even less trial sites. Usually for a standard muon calculation, we have the tens of trial sites. So now we can confirm the workflow settings, and we are again on step 3. So the choice of computational sources. In this case, we have mainly 3 code that we use. The first one is the usual PW for the DFT relaxation. Then we have PP, which is basically a post-processing code of still of the quantum express package, which is used to compute the, in this case, the spin resolved charge density. That will be then used to compute the magnetic interaction between the electronic charge and the muon. And then we have this Python job, which is basically a Python executable, which can be used to compute the muon spin polarization by means of the UNDI package, which is a Python-based software. Then once we are happy, we can submit the simulation. Also, in this case, we just download a pre-computed example. So we go back to download examples page. And the example that we want to download is just this one that you see here. So lithium fluoride and Muon in-app guide sites. And once it is downloaded, we can go to the calculation history page to find it and open it. Here. If you have a lot of simulation and you don't know how to find a given simulation, you can also use filters to like query for calculation with a given label. For example, Muons, and I see that here I have my simulation. So now what we see is that we have indeed a Muon result tab. We open it. And basically what we obtain is the main result is basically a table with a collection of all the Muon sites that we tried, ordered by relative energy with respect to the lowest energy configuration. We can also visualize all the, in this case, all the 3 of the candidate sites. We can inspect the structure by computing the distance between the muon and the neighboring atoms. And in particular, what we can observe is the distortion induced by the muon. This is crucial if we want to discriminate between different muon sites. And here what you see is indeed, for example, that the first muon, the muon A, so the lowest energy configuration, basically let's say pulls the lithium, the fluoride atoms and pushes the lithium atoms. As basically also already shown in the literature. Also, in this case, we can download all the data. Basically, we download all the structures and the table, and also all the data on the distortion. Questions? Yes?
A general question. Do these calculations and you want to change something and rerun them, can you do that?
Yeah, so basically the question is if we can change a parameter and submit the calculation. So yes. So basically the calculation will recompute all the sites now, but it's also possible to actually to upload the structure with already the muon inside and compute the relaxation and then the polarization. So in principle,
So I cannot take something from my history, from the history of my calculation, change something, and resubmit it.
No, up to now we don't support this, but it's actually one of the next improvement that we want to do in the app, to implement in the app, because it's indeed a very useful.
Yeah,
Wait.
it fails sometimes. You get calculations which fail. You don't know why.
Exactly. Yeah, I agree. Yeah, thank you.
You can come there, please.
Yep.
And this is also an answer for the previous question, which was kind of similar. How can we go in the history and restart with some modifications? This indeed is in our plan, is the next one of the next features. Realistically, I think in 2 months we'll be there. And indeed, it could be just because you want to rerun it. Maybe you want to rerun on a different supercomputer because you realize it was too slow, you want to change. But also, if you want to do convergence of parameters, if you really want to do it, you can just reload it and change only the K points, change only the cutoff. So we are trying to consider all these approaches. And so I say how we want to do it. So if you have feedback, it's welcome, and then we see what can be done. The idea would be that you run it once, and then you can go in the history and use it as a template. And then you can see all the parameters and even possibly specify a range for a parameter. So if you want to run K points 16, 18, 20, you can run 3 of them. That's a bit what we envision. This will take, again, a couple of months of work, all included. So we hope in the next release in the summer, this can be possible. So if your use case is similar but slightly different, feel free to let us know, either in person or we'll give at the end a feedback form so you can type it in. Because I think if we realize there is a slightly different use case, we can cover what a slightly different interface. We support it out of the box. Otherwise, it goes through longer time for development.
Yes. Okay, so basically, this is what I wanted to show you. So we just completed the most of side by means of this P plus view, and I showed you how to inspect the results. And basically, next steps are contained in the post-guide exercise in the in-app guide of the app. But basically, the next step would be to compute also the spinner acceleration function for the same system. So that's it. Xing.
Okay, so hello everyone. I'm Xing Wang, and now let's talk about a little bit about bar charge calculation. So a bar charge analysis is a method to assign electron density to atom in a molecule or solid. So it's a very simple but very useful tool. It can give you the insight, for example, the charge transform between the atom, such as the mental support interaction in catalyst, or understand the oxidation state, and also the bonding nature in the molecule and solid. Or you can useful for the interpretation of the spectroscopy data. So in this tutorial, we will try to run boundary charge calculation for 2 systems. One is platinum 2 oxide, another is platinum 4 oxide. So, okay, so this is the calculation page. Again, we can go to the tutorial, and we can switch on the boundary charge analyze tutorial. And then we can follow these tutorials in-app guide step by step. So first we go to from the example and select the boundary charge. And here you can see the 2 structure, platinum 2 oxide and platinum 4 oxide. We select the first one, and then we confirm it. Again, so we choose not relax the geometry for this tutorial, but of course in the production run, you can always you are suggest always run the geometry optimization, and then go to step 2.1. Here you can select the bother charge analyze, and then go to next step. So the tutorial for this, we choose fast protocol and the insulator electronic type for the system. It also provides a bother charge fitting panel, but as you can see, it's quite simple. Basically, user don't need to fit anything for it. Here, there is one option that you can choose the pseudo potential like PBE or PBE4 group, but I just suggest you use the default value. So basically, quite simple. Yeah, and then you confirm it. Here we have 3 codes to fit. One is the PW used for the SDF calculation. Another is the PP for the post-processing. And another is the bother charge, like the bother code. Normally, if you run a big system, you need to use more CPU for the PW calculation. But for the PP, you can use less CPU. And for the bother code, one CPU is enough. And then we can submit the calculation. So for this simple example, it takes around 5 minutes to finish. And because people already asked how to submit the calculation, so I will submit it now. Just click it, submit. After you submit the calculation, you will automatically go to the step 4. And in step 4, you will navigate to this data panel. And here you can monitor whether the job is running or waiting or it's already finished. So you can see here we have a bother charge workflow. You can inspect the more detail of the calculation. For the first step for this bother charge is the SCS calculations. You can click it and you can see the output of the PW calculation. Okay, so once it's finished, you can go to the result panel, and you will see it tell you that the state, okay, the job is running. When it's finished, you can click this load result button to check the result. As I said, this calculation takes around 5 minutes, so we just go to the example. We can import it directly. So here I provide 2 examples. One is PTO, another is PTO2. So you can select them and import. And then you can go to the calculation history, and then you can see indeed your job is imported and finished. And because I already imported, so I just show you the result directly. Yeah. Okay. So the result panel is also quite simple. So it just show you a table for the list all the sites. For example, here we have 2 platinum atom and 2 oxygen atom, and then you have a table with 4 atoms. And when you can select the row, and the atom, the selected atom will highlight it, right? And then you can check the most important result is this one, bother charge difference. So this bother charge difference is the difference between the calculated bother charge and the neutral state. The neutral state means we count the number of the valence electron in the pseudo potential, and then we calculate the difference between the actual bother charge and the valence electron. So you can see here for this platinum 2 plus, the bother charge difference is 0.82, and for the oxygen is oxides, the minus value. But we can also go to another calculation for the platinum 4+. So here you can see that we have 2 platinum and 4 oxygen, and the boundary charge difference is around 1.5 for the platinum 4. Okay, so now we have the result, right? So this is for 2+, and this is for 4+. You can see it already gives you some insight about the oxidation state of the species. In reality, in the literature, people can use this charge as a reference to get the insight of the oxidation state in the realistic system. Here I show one example of the catalyst. So here is a platinum oxide, no, sorry, not platinum oxide, it's platinum nanoparticle supported on titanium oxide. And in this paper, they calculated the charge density difference, okay, to show where charge accumulate and where charge is decrease. And it often calculates the boundary charge. You can see that because as shown in the table, right, we can get the boundary charge for each atom, right? So you can plot the boundary charge, the distribution, so you know, okay, where charge transform from, whether it's transformed from the support to the nanoparticle or from the nanoparticle to the support. Okay, so this is one example. Yes, so that's the end of this tutorial. So any question on this part? Okay, if there's no more question, then I will go switch to the next part. It's how to continue human. So should I? Okay. So the next part I want to introduce is that when we finish this course, so how to continue use IR lab in your future work. For the moment, you run your calculation in the online deployment, right, on the survey. But we also provide a way that you can install IR lab in your local computer. As part of some of you maybe already tried, especially for people online, you may already install IR lab on your laptop. So I will give you some quick but overview of it. So for IR lab, we provide a Docker image, which has a pre-configured IR environment and all the necessary software, so you can run the calculation locally. And for different systems, we often suggest different way to install it. For Linux and Mac user, you can use IR lab launch tool. And for the Windows user, you can use the Docker desktop, the GUI. If you also familiar with WSL in Windows, you can also try to use IR lab launch tool. For some advanced user, which you want to customize your own volume and other settings, you can try the Docker CLI directly. So all the detailed instruction you can find in this online docs. So here I give a quick overview. So for people installed the Docker desktop on Windows. So first step is to find the image for the IR lab, specifically for our calculation in the IR lab Context Explorer app. So in this one, IR lab QE. So you can search it in the search bar. One important thing I want to highlight is you need to create a persistent volume in your computer and mount it to the Docker container. this is important because when you run some calculation, your data is saved in this volume. If you don't create a persistent volume for it, when you close your container or shut down your computer, you will not have your data anymore. So it's important to have a persistent volume. When you set up all this, you just start the container, and then it will provide you the URL, and then you can open it on your local browser. For the IDLab launch tool, if you run on Linux or Mac system, so you can use pipe installed to install IDLab launch, and then you create a profile using the IDLab QE image, and then you can start the container. It's quite simple, and most importantly, this IDLab launch tool will create the persistent volume automatically for you, so you don't need to worry about this. Sorry?
Yeah. So I say to Xing, you can repeat it. The slides are going to be online already. The slides until last Monday are already online with the video recording. And these instructions is what we sent anyway by email on the weekend. You can repeat it. Xing, you can repeat it maybe for the speakers. You can see it again.
Okay. Yeah, so all these slides will be uploaded and also sent to your email. Yeah. Okay, so there's another way, apart from the local installation, so we also provide some cloud deployment. So you can check the some official cloud deployment in this website. And specifically for people who work at PSI, we provide PSI internal deployment. So you can go to this URL, and then you can log in with your PSI account. If you have any issue when you log in or use this service, you can contact Miki, and here is the email address. Okay, then assume you have your access to IDLab in your future work. There is another important step is to set up the computational resource. So for most of the DFT calculation, it's quite expensive, especially for realistic application, right? We need supercomputer to run it. But how we make the collection of the local IDLab instance to the remote computer. So in the app, we provide a page to set up the communication resource. So when you, maybe I can go to the demo. So on the home page of the app, you can click this setup resource, and it will open another page. And in this page, you can follow the instruction to install or to set up the computer and the code. But the most important thing I want to see is that, okay, go back to the slide. So we provide two ways to do this. The first one is quick setup. We already pre-configured some of the computer, like the Merlin cluster in PSI and the Swiss National Computer Center. So we already provide the configuration file in this IDA resource registry. And for the app, it will load the config file directly to the page. So you can select it. For example, I can select Eiger or Muon, right? When you select it, you can choose which code you want to set up. For our calculation, we use context espresso, so you can choose context espresso. And the next step is to select the code for each for each calculation. For example, the PW we use for the SCS calculation, or basically we need it for all the QE context espresso calculation. So you can choose this one. Of course, you can set up other like PP, PH, DOS. So when you select it, you input your username for this Muon PSI cluster. It's just your PSI account, but you need to request to have access for Muon online. I will show you later so how to do this. And then you just import your password. And then you can click quick setup. So oh,
Yeah, it's just because this virtual machine is not in the PSI network.
okay, yeah, okay, yes. So you because this is not in the PSI network, so this not in field. But when you run it on your local computer or at PSI, you can see it very quickly. So this is how to do this setup. Okay. After you set up the code in your actual calculation, you can select the code in the step 3. So I can quickly go to step 3. So you can select the code in this step. Okay. So what if my computer is not in the quick setup? So there are 2 options. The first, you can add your resource to the IDA lab IDA resource registry repository. So in this link, you can make a PR to add the new computer and code. But if you don't know how to do it, you can simply open an issue there, and we will see it, and we can help you to set up the resource. And option 2 is you can also manually set up in the page. To do this, you just click this checkbox, and it will open a new box to where you can set up the computer manually. So the first step is make the connection between your local computer and the HPC. So you input the host name and the port and the username and password, and click set up SSH. So that's a very very simple. As soon as you have the connection, you can set up the computer more detail, that what is the folder you want to save your data, and how many CPUs for your HPC, and so on. And when you finish the setup with the computer, you can set up the code, for example, the PW code. In this setup, you need to tell the IDA so how to find your code, how to find the PW. So some maybe you need to know some module, and where is the path of the command. So you can see that there are many fields you need to input, but don't worry. So you can check the example in this IDA resource registry, and then you can find some template. You just follow that template and modify some of part of the variable, and that's it. If you have a problem, you can either contact the HPC administrator, or you can also open an issue in our repository, and then we can help you to solve the issue. Oh, the final thing is for PSI internal user. So if you want to use Muon cluster, you can go to this page, and request the access there. Yeah, so that's this part. Finally, we also provide the documentation link here, and also for the GitHub repository. So feel free to go there and check. Any question for the moment for this part? Yes.
About the PSI user, so you're providing an access to Merlin, PSI internet. Is there a specific way to do it for the PSI?
Sorry, my hearing not that clear.
So I see that you have a way to connect PSI internal users to Merlin.
Yeah.
Is there a similar way for PSI users?
For the EPFL user, I think first, if you can access internally, right, from EPS or APS, then you can also input the host name and do the them. Yeah.
From here because it was recorded. So the question was about access also for EPFL users. So I think what Xing showed is it works for any computer. So you can just, as long as you know the host name and you can access it, it's going to work. If you run from our test server, it's not going to work because typically these supercomputers require that you are inside the network. But if you run it from, you install IDA Lab on a computer inside EPFL or inside the university in general, your laptop or even a workstation you have in the office, then it's going to work. We have the predefined options. They just are a registry of codes we maintain, and it's on GitHub, so anybody can contribute more. So if you discover that you and more users want to set up the same supercomputer at EPFL or in a different university, that's what we did for Merlin. It's just a matter of you configure it once, you make sure it works, and then you can make a PR or even just write us, we can help you. So in the next release, people see also all the EPFL supercomputers with everything set up correctly, so it's much easier. But it's not required somehow, it's just a convenience. For EPFL, I think we can do it for sure. Other questions? Okay, so we're getting close to the end of today. We'll probably finish a bit earlier, so we can get more coffee. But for those of you inside here in the room, we are here until 5, so feel free to stay and ask more questions if you have specific questions. For those online, you still have another 15-20 minutes to ask on the Q&A if you want. And a reminder, we will turn off the machines tomorrow at noon. And we also stop monitoring Slack tomorrow at noon. So if you have a question, please ask today or tomorrow early. In any case, there are standard channels for AIDA and AIDA Lab support. For instance, you can go and search for AIDA Lab. Sorry, I'm gonna come here, don't worry. You can ask for AIDA Discourse. There is a channel where you can ask questions about AIDA, AIDA Lab, and so on. What I wanted to give in the last 5 slides, essentially, is an overview of other plugins that we have been developing, and we didn't have the time to present today. Some of them are already production ready, some are, but essentially XPS is one example, XPS and XAS. Others, which I present in the next slides, are just being developed, so are almost already working or almost working. But just to give you a sense of the direction in which we're going, maybe because if it's topics which are interesting also for you, you already know these are already existing or going to appear online very soon. So the first one is another plugin to do similar to what you have seen until now, another set of calculations, also using Quantum Espresso for core level spectroscopy, in particular for XPS and for XAS. So we have both plugins. Internally, they use some similar technology. In particular, there is a symmetry inequivalent site search. So when you create a supercell and then you make an atom, want to remove, essentially simulate removing a core electron from one of these atoms. This was done by taking care of symmetries and only computing symmetry inequivalent supercells, which make it much more efficient. A bit similar to what we have already seen in other tools where supercells are created, but with a slightly different algorithm. Again, they are all using quantum espresso, so the method is based on, again, a supercell approach, and it uses core-hole pseudopotentials. So you remember from my lecture 2 days ago, quantum espresso uses pseudopotentials to ignore essentially the fact there are core electrons, which is instead something, of course, you need for level spectroscopy. You're removing an electron from the core. And the way this is simulated in this pseudopotential-based codes is essentially you have 2 pseudopotentials, one, the standard one, which will have all the electrons filled, and one which essentially simulates a situation where an electron has been removed. So you need to provide these special pseudopotentials. We provide a few for some selected elements. More can be generated that would require some collaboration with us or other people who know how to generate pseudopotentials, in case you will need more. They are, of course, less tested than the pseudopotentials, standard pseudopotentials, but we're planning to do an effort of also generating libraries in the next years of core-hole pseudos. So it's just, again, a matter of clicking around and starting new simulations. Here you see 2 examples of the output, which is relatively simple, but allows you already to predict and compare experiments. One important thing, especially at the exact level, we are not using GW in this simulation, so it's standard DFT simulations. And what I want to highlight, the workflows have been developed in collaboration with CNR Nano in Modena, in Italy, in particular the group of Dr. Deborah Pizzi, who has been leading the development of the underlying workflows for these 2 tools. So that's one, and they're actually already available. So if you go in your app, you go in the plugin registry, you can install it, and then you can start running some simulations. The second plugin that is just been released and developed just a few weeks ago, essentially, is a plugin to compute Wannier functions. Essentially, it's a plugin that allows you to automatically compute Wannier functions for any material based on the method developed by us, by especially Jungfen Chao, our PhD student now just graduated, and Nicola and me. It's called the projectability disentanglement Wannier functions. And the current plugin already implements those for computing the Wannier functions themselves, showing them in real space, and comparing band structure interpolation. And of course, also downloading the corresponding Hamiltonian in real space. This use also other methods are supported, like SCDM method, which is another method also to compute automatically Wannier functions. But actually, in terms of outlook, we're just finalizing now another paper where we also extend this method to spin orbit coupling and to magnetic systems. So the first implementation was only for non-magnetic systems. So this is working, and the paper is going to be out in a few weeks. And so we want to make sure that also this extension is going to be part of the app, so you can also compute Wannier functions for magnetic systems with or without spin orbit. Another thing that we did some additional algorithmic improvements, and actually in our test cases, this extended PDWF algorithm as essentially 100% success rate in obtaining Wannier functions, which we're very happy with, because until last year, essentially, it was a manual process to get Wannier functions, and now we can do it automatically. So that's a number of things we want to add in the application in the next few months, or weeks or months. And of course, once you have Wannier functions, you have access to a large number of properties that you can compute with Wannier functions. If you don't know what Wannier functions are, essentially, you can access many properties like topological properties, etc. But one important thing is that it becomes a very efficient interpolator. So you can compute DFT at the DFT level, band structures in a Brillouin zone with just, maybe 10 by 10 by 10 grids or 15 by 15 by 15 is still reasonable. And then you can interpolate them back using Wannier functions on 100 by 100 by 100, which in DFT would be essentially unfeasible, very inexpensively. And so you can start accessing properties which depend on very dense integrals in reciprocal space. For instance, if you have integrals which are very sensitive to what happens close to the Fermi level, to the Fermi surface, these are very thin volume in 3D space, in reciprocal space. And you need really 150 by 150 by 150 grids to really have converged properties for transport, Boltzmann transport, and many of these properties. And therefore, using Wagner functions is very important. Properties we've already been working on include computing the Fermi surface. So this is something which we want to add as one of the first features. And once you know the Fermi surface, using codes to compute, for instance, the Haas-Van Halfen and Shubnikov-de-Haas association frequencies, if you put your sample in a magnetic field, varying magnetic fields. But there are many more properties we can add. So if you have tools that use Wagner 90 or output of Wagner 90 to compute property, topological properties, etc., which would make sense to add to the app, this would definitely be something that you can let us know in the feedback form or later, and we can consider if it's something we can add easily or not. Okay. And finally, a third example, which actually is already there, but is not fully functional, so will be fixed in a few weeks. But essentially, it's already implemented. So you see the actual GUI is the automatic computation of Hubbard parameters, so dft plus u and dft plus u plus v, so the value of u and v, automatically set consistently using density functional perturbation theory. So the same theory would use to do phonons, not the one you saw today, because it's based on finite differences and phonopi, but the one implemented into quantum espresso. So the idea is that often, we already discussed this a few times, I think, in this course, but often one just takes a value of u and puts it in the input. That's what also you saw earlier. And that's already supported, but there is a way, a method developed by Yuri Timrov, Nicola Marzari, and many other co-workers about how you can compute the u self-consistently and also the v, the intersite. And this is specific for your material and it's very accurate. This allows, for instance, to get very correct voltages for cathode materials and so on. And in order to do this, there's a new code which has been part of Quantum Espresso in the past, I don't know exactly 1 or 2 years, probably HP. And very recently, just a few weeks ago, the workflow in AIDA has been published by the authors here, so Nicola, Yuri, but also Lorenzo in Bremen. So the workflow is available, and we also already developed a GUI for it. So you can now just put your structure and say, oh, I want to compute in this specific structure, for instance, the U for cobalt, and also the V between cobalt and oxygen 2p. Cobalt here is 3D and oxygen 2p. You just click the box, let it run, and the simulation will run for you and return the value of U and V that you have to use, that then you can use for your simulations. Okay, this concludes a bit the highlights of AIDA Lab, and in particular of what features you can do now already with AIDA Lab and the AIDA Lab Quantum Espresso app, and a bit of a sense of what are the very next features we're going to provide. We hope you enjoyed it. We hope it was useful for you. Everything, as was already mentioned before, it will be online. Already the slides and the video of the first 3 days are online if you go on Indico. They're on YouTube and you can download the slides. Hopefully even later today, we can put on YouTube also the one of today. In any case, we are going to create a new section in Materials Cloud Learn, where the slides and the material will be available also for the future. So who is going to watch this in the next months or years. And one final thing that since we have some time now, we really appreciate if you could do it now. You can just scan this QR code and fill in the 6-7 questions essentially, but most of them are checkboxes. I think it really takes 2 or 3, 3-4 minutes, let's say. It's what we ask you in exchange of the coffee outside. But also for those online, we'd really appreciate if you could open this link and fill the form now, because this will allow us to get a sense, was the course too easy? Was the course too hard? Should we take more time to do the theory? Should we take more time to do the demo? Are there parts you would like to see more represented or less? So that's it. I think we wait 2 minutes so that people fill the form, and maybe we just conclude with maybe some quick final questions from the audience if they have any. But already, if you have questions now, we can already ask, of course.
I have a question not directly related to DFT, but to the interface itself. So first of all, thank you for creating and introducing this tool with us. So I like the organization of experiments and setting parameters and whatever. And I would actually be happy to, make a similar interface for the experiment, like the instrument that I'm using. For this purpose, what would you suggest?
Yeah. So I repeat the question for the audience. So as a general thank for the interface, and the question is it possible, is it easy to also do the same interface, but not for DFT simulations, but actually for controlling an experiment, correct? So what we're using is Jupyter, so standard Jupyter, which means that once you have it, as long as your institution provides a Jupyter Hub, or you can deploy a Jupyter Hub, which is, okay, if you never did it, it's complicated. If you know how to deploy things, it's standard, it's documented. That's easy to do. Now, Jupyter wasn't designed by scratch to make graphical user interfaces. We have been working on IDLab for quite some years now, and we have been designing also guidelines on how to design proper GUIs, like a standard pattern, not something we invented. It's a standard pattern, like if you know GUI design, MVC. So the better ways to not just hack it in, because also for us, when we started 4 or 5 years ago, we started with tests, and now we have a proper way to do it, which is easier. There are new ways which are testing, and hopefully we will have a demo in a couple of months. There's a new technology called Solara, which uses Reacton behind the hood. So for those of you who have heard about React in JavaScript, it's the kind of Python equivalent, which makes making GUIs much easier in principle. You have to spend one day figuring out how it works, but then in the end, it's way easier. And we are going to investigate how to use Reacton and Solara also for apps as one alternative. So that's just a general answer. Now, specifically, it's possible. I can point you maybe to some links. Actually, we have in AIDA. Let me see if I can show it here. Actually, there's also. So AIDA is the underlying workflow engine behind AIDA Lab. And we have been starting since last November to have blog posts. So every 2 to 3 weeks, we will have a blog post, sometime on AIDA, sometime on AIDA Lab, it depends. And actually, we have a LinkedIn channel of AIDA. So if you are LinkedIn, you might want to search for AIDA and follow us, because you can get this notification and more information about AIDA and AIDA Lab. And in addition to something which we kind of presented here, there is one which I hope I find quickly here: design principles for AIDA Lab apps. So this already is a short blog post written by Idan, which essentially explains how to properly design a GUI in a way which is easier to maintain. So that could be a nice first read. One more thing I can say, with Miki, we have been collaborating here, PSI, with Experimentalist, exactly to not only use AIDA Lab as a GUI for AIDA and for Quantum Espresso, but to actually look into the data of the experiments. One collaboration, for instance, we are running now is with Kamea, an experiment in the neutrons, where they have this Mjolnir software that they use to reconstruct the neutron data. And now there is an app from their lab where this can be done live. So you can get the data. And so on one side, it makes it much easier. You don't have to install Python in the libraries, but everything is there. You click a button and it works. But also, since it's here at PSI, we are working on a deployment which is connected to the data. So the experimental data goes directly on NFS, and we can mount the NFS in the AIDA Lab instance at PSI. So that's what something we'll be configuring. And we also speak to the digital user office database, the Duo, that whenever you come to PSI, you get access there. And so we show every user only their own data. So in the machine, you don't have to get the file from somewhere else. You have a folder with all your experiments. If you have more than one proposal, you just click and you see the GUI, and you can live, essentially, almost live, see the experimental data coming out. In this way, you have in the same platform AIDA Lab, both the DFT part, but also the analysis of the experiments. How long it takes, it depends. It depends if you already have a code, what's your experience in programming. So I don't want to say easy or complicated. Once you know how it works, adding these GUIs for us for the experiments took half a day. I mean, we had another one with Icon on neutron imaging about getting an image and we histograms of an image along X and Y. This took me and Miki a few hours in the end, once you know what you're doing. Okay, so let me go back here. Okay, so I hope you had time to fill the form. Thanks. Before we conclude, are there more final questions?
Maybe two short
Yeah.
questions. Maybe one, now that we towards the end mentioned external potentials like magnetic and electric fields, and we didn't touch on it at all. I don't know how much, as a layman, DFT, I don't know how that could be incorporated in.
Yeah, that's an excellent question. So the question is about how to incorporate external fields like magnetic and electric fields. So there are different ways. Maybe I speak for electric fields first. So first of all, we don't support them yet in the app. You can do it with Quantum Espresso, and you can do it with AIDA. So if you use the command line AIDA, it works. But we don't support it in the GUI yet, because as you can imagine, the GUI is a bit limited and we have to make a decision. But if we have many users asking for it, we can think about it. There are two ways essentially to do it. One is to essentially, when you put an electric field, your potential becomes a linear term, where the slope is the electric field. Now, this is not periodic. It's a line. If you have periodic boundary conditions, you cannot make a periodic line work. If you have a material which is not bulk, but is a layer or a wire, then what you can do is use like a sawtooth potential. So essentially, you put the linear part of the potential where the material is, you have charge density, and between the layers, we have no charge density, you jump down. And so instead of having a constant line, you have something going linearly and then down, linearly and down. The important thing is that where the potential has the jump, you don't have any charge density, so you don't have any physical effect. And you have parameters in Quantum Espresso to say where the potential has to jump. There is a better way using enthalpy, where essentially you can actually impose a condition of having a field and compute the effects of a field. And it's a different input setup. This is a very phase, something a bit more advanced we didn't discuss here. And it's used internally in the Phonon workflows. So when the Phonon workflows computes electric field effects for the electric constant connectivity charges, it uses this internally. Again, apart from the Phonon which does it internally, is not exposed, but is possible with Quantum Espresso. Magnetic field is a bit trickier. Sometimes you also have to think about making supercell commensurate with the field. It's also something, again, is not supported here. And I have to say, I'm not even an expert myself, so I don't want to say something wrong. It's possible, but it's a bit more advanced. You had another question? Yeah.
Yes, maybe a small general one. I don't know, but well, of course, these computations are made expensive, and heuristics that are given fast, stringent they're chosen for a reason. But how strongly should we feel about clicking the submit button before we, thinking about environment?
So it's a good question. So the question is about the cost of DFT simulations, and even if there are protocols like fast, balanced, and stringent, what should one think about before hitting the submit button? It's an excellent question. I would say the last part, which to me is very important, but it's very tricky and also maybe not so scientifically exciting. And so the hard even to find funding is to have a predictor or a heuristics for the time for a simulation. Simple things exist and one can do it. And actually in the app, there are some indicators. So there's a warning that can pop up if you do something which is clearly too expensive. If you have maybe more than a given number of atoms or more larger than a given volume on a simple machine, it will tell you probably it's going to be too slow. I think it would be very interesting to add it, because indeed, if you have never run it, you have no idea if it's going to take 1 hour, 1 day, 1 month, 1 year, and if it's 1 year, maybe 1 month you don't run it, and how much it's going to cost in the end. Of course, once you start running simple examples, one thing you can do is to submit it. And after a few minutes, you start looking at the output and you see, that's what we would do now. You start seeing how it works. Or use basically heuristics based on the scaling of DFT with the number of plane waves, the number of electrons. There are power laws, and you can get a sense if you double the number of K points, what happens, etc. One work which actually was very interesting a few years ago, and it's been a bit discontinued, was a colleague of us, Pietro Bonfa, actually one of those behind the Muon workflows, who developed a predictor of the time for a DFT simulation to run. It was very interesting. Essentially, given the input, would predict the time per SCF cycle. And there's been always the hope, the idea of converting it, maybe nowadays also using machine learning to have a heuristics that tells you, okay, with this input, I think it's going to run for this long amount of time. And for me, even more than absolute time, which is harder to predict, you don't know how many iterations there are, you can get an order of magnitude list, which is good. What is interesting is also that there are many parallelization options when you run these codes that are in the code, and we expose partially also, that can be very important. So not only you say, okay, please run on not on one CPU, but on 20 CPUs, but you can also say, oh, divide the calculation in two pools. So you run actually in parallel, one K point in one pool of 10 and one K point in another K pool of 10. And you try to optimize in a view 20 or 10 plus 10 or 5 plus 5 plus 5 plus 5, etc. This can change a lot the time to solution. Also, but this depends on the size of the system, how well your system is parallelized, etc. There are no rules. Also depends on the system which you run. So you change supercomputer, this might change a bit. Maybe the general rule I give here, because it's also an option which is exposed, these K pools are very important. When you parallel, if you remember the DFT lecture, when you run on K points, every K point is independent. So as long as you have enough memory, you should use as many K pools as possible, because all these runs are independent of each other. So if you have 4 CPUs and you have to decide what to do and you have enough K points, you should use 4 pools. So every K point runs serially, but 4 run at the same time, and there is almost no communication. Only at the end, when you sum to get the charge sensitive, things are summed. The other option, the extreme opposite, is to run the essentially parallelize diagonalization and parallelize FFT on 4, but this requires more communication, so it scales less well. So if you have 4, it's also important, but if you have 128 CPUs, unless you have a very big system, it's not going to scale. It's not going to be much faster than running with 16. But if you have many K points, you can run 16 times n K pools. So that's something to, the main thing, the easy one. Then there are 3 or 4 more parallelization levels in quantum espresso, and this one has to typically try and optimize. Okay. Great. Final questions? If not, thanks everybody again. Thanks also to the online audience. And we hope that you're going to use it. And for PSI people, there is another session on 29th, 2 to 4. We send an email. So if you want to come and have more questions in 3 weeks, we can come and speak to us. Thank you.